We want to determine if the graph represents a polynomial function, and if it does, we want to answer the follow-up questions. The graph that we see here is a polynomial function because it is continuous, it has smooth, rounded turns, no sharp corners, no breaks or gaps. So this is a polynomial function graph. So to determine the minimum degree, we want to count up the turning points of the function. So the turning points are where the graph changes from increasing to decreasing or decreasing to increasing. These are the peaks and the valleys of the curve. So if I look at this graph, I have a turning point down here, another one up here, and a third one here. So this graph has 3 turning points. So the minimum degree of the function is always going to be 1 greater than the number of turning points. So for A, the minimum degree would be a 4th degree polynomial. That should make sense if you focus on the fact that this graph rises and rises like x squared. So it would follow a even degree function behavior, and the minimum degree would be 4th degree. Let's determine if the leading coefficient is positive or negative based on the end behavior, and if it's even or odd. So that leads us into the end behavior. Since it rises and rises, then we know it's an even degree function like x squared. And since it's rising, then we know that the leading coefficient would have been positive. If it fell on both ends, it would be negative. The real zeros of the function would be x equals, and we're going to look at the x coordinates of the graph. Where is it crossing or touching the x-axis? So if it bounces off of a point, it is an x-intercept or a 0. So this graph has an x-intercept at -4, -1, and +3. So these would be the zeros of the function. Your textbook may list the zeros in a roster where it says that the set of zeros are inside. You do not have to list your answer like that. Here's another graph where we want to determine if it's a polynomial function. So if we look at this graph, if we trace the shape of the graph, we can see that as I come down, it has a sharp corner, and then it has another one here. So because of those sharp corners and turns, it's not rounded and smooth. This is not a polynomial. So you would not find the follow-up information for this function. For this graph, if we trace the function, we can see that it is continuous and it is smooth, no sharp turns. So that is a polynomial function. So let's go ahead and find out what the minimum degree would be. So we want to calculate and count up all of the turning points on the graph. So turning point is where it changes from rising to falling. So here's one turning point. There's 1, 2, 3, 4, and 5. So then the minimum degree would be 1 greater than the amount of turning points. So this would be a minimum degree of 6th degree. Always 1 greater than the turning points. So to determine if it's even or odd, we want to look at the end behavior. So I can see that it falls and falls. So when the ends match, it's always even. And since it's falling, I know that the leading coefficient was negative because this matches the end behavior of -x squared. The real zeros are where the graph crosses or touches the x-axis, so I can see that happening at -4, -3, -1, +2, and it looks like 3.5. So let's list those out. -4, -3, -1, 2, and +3.5. For this graph, it is smooth. It has rounded corners, but it's not continuous. This hole means that we have an undefined point in the graph. So whenever we have a hole or we have a gap, it is not a continuous function, so this would not be a polynomial function, and you would not find out the follow-up information for that graph.